All right, we've used the first derivative to find relative max, relative min. Now we're going to learn how we can use the second derivative to find things. So I've got up on the screen what we should already know about what the first derivative does for us. Okay? Now, just a quick reminder, hopefully this is a little bit of a duh moment, but the second derivative is the derivative of the first derivative. So all the things, well, let me stop myself there. I want to get off on a tangent. So that's what we already know. Extrema occur at critical numbers. That's where f prime of x equals 0 or f prime of x does not exist. We know that if f prime of x is positive, that means our function is increasing. If f prime of x is negative, that means our function is decreasing. And then the vice versa, right? If you know the function is decreasing, you know the derivative is negative. And if the derivative equals 0, you've got a horizontal tangent line. If the derivative always equals 0, you've got a constant function. Where the derivative changes from positive to negative, that's where you have a relative maximum. Where the derivative changes from negative to positive, that's where you have a relative minimum. All right, so let's go on to what the second derivative can do for us. The first thing we're going to talk about is concavity. The definition of concavity on page 190. Let f be differentiable on an open interval. The graph of f is concave upward on that interval if the derivative is increasing on the interval. The graph of f is concave downward on the interval if the derivative is decreasing on the interval. So, if you look at the graph here on the left that you see on the screen, as we move from left to right, the slopes of the tangent lines get larger. That means the derivative, which is the slope of the tangent line, is increasing. Okay? So see, like here, where they draw that one in, that's the slope of that tangent line is actually negative. And then over here, the tangent line's positive, so the derivative got bigger, didn't it? It went from being negative to positive. Positive, and that slope steeper, so it's even a bigger number. So as you can see, as the graph is what we would call concave up, all right? That's concave up. The derivative is increasing. And a good example is what the book's done here. A good way of looking at it is by slopes of tangent lines. Think of the derivative as the slope of the tangent line because the derivative is the slope of the tangent line. And what's going on is as you move from left to right, the slope, every time you've moved over to the right, the slope gets bigger. Therefore, the derivative slope is increasing. So whenever the graph is concave upward, the derivative is increasing. Whenever the derivative is increasing, the graph is concave upward. That's the definition of concavity. And then with concave downward. So here we've got concave down. Okay, look at the concavity, not whether the function's increasing or decreasing. Because look, you can have an increasing function with downward concavity. That would be, wouldn't it? That function's increasing, but that's downward concavity. So don't confuse concavity with increasing and decreasing for the function. Concavity goes with increasing or decreasing for the derivative. Keep them straight. No. That derivative is positive and fairly steep. That derivative's positive, less steep. See? Whenever the derivative is decreasing, then we have concave down. Whenever we have concave down, the derivative is decreasing. Do you see that on that graph right there? That's what's going on, isn't it? Does the concept make sense to you? Now, you're going to have to memorize it, because if you have to figure it out every single time you're faced with this, you're going to make these problems really long, and eventually you're going to make a mistake. So it has to make sense. And then once it makes sense, just remember the relationship. Concave up, derivative increasing. Concave down, derivative decreasing. Okay? All right, now, let's think a little further. If I've got, I just want to stick with this one here. If I've got concave upward, look what's going on here. I've got F is concave up, F prime is increasing. Let's take this a step further. I wonder if I can tell anything about the second derivative. If, well, think back to what we did before this moment. If I told you that a function was increasing, wouldn't you be able to tell me right back that means its derivative is positive? That's what we learned back in the previous section when we were working with first derivative test, right? So if I tell you that a function is increasing, f prime is a function. So if I tell you that a function is increasing, shouldn't you tell me that means its derivative is positive? So f being concave up, and in fact, let me write it this way. F being concave up, that's an if and only if symbol, goes with f prime increasing. F prime increasing goes with its derivative being positive. Those three things always go together. If I tell you the second derivative is positive, you should be able to tell me, oh, that means the first derivative is increasing, and then by definition, that means the function is concave up. No, the function itself being positive has nothing to do with anything. You got to stick with what we've got here, okay? Don't drift afield here. A field, drift. You don't drift afield. You drift away, afloat, out there. So don't try to generalize this past right here, because this is as far as it goes. Don't overgeneralize. All right. Tell me this then. If f is concave down, what's that tell us about f prime? F prime is decreasing. And whenever a function is decreasing, what does that tell you about the sign of its derivative? Negative. So that means f double prime is negative. So everything in black goes together, everything in blue goes together. How often does everything in black go together? Always. How often does everything in blue go together? Always. You can jump in there anywhere. You can start in the middle with f prime is decreasing and conclude both those other things, that the second derivative is negative and that f is concave down. You can start at the right end with f double prime is positive and work your way to the left. F double prime positive means f prime is increasing, means f is concave up. You follow me? Does all that make sense? Okay. I didn't mean to be so gruff with the don't overgeneralize, but you can't go, well, let's put it this way. You know what you know. And what we're talking about is the concavity of the function, not whether or not the function is increasing or decreasing, not whether or not the function is positive or negative. Okay? We're not even talking about whether or not the first derivative is positive or negative, are we? We're talking about the first derivative increasing or decreasing. And for the second derivative, we're not talking about whether it's increasing or decreasing, are we? We're talking about whether the second derivative is positive or negative. So don't switch categories. Don't make a category error. Okay? Function, concavity, derivative, increasing or decreasing, second derivative, the sign. Those are the things that go together. You with me? Okay. Now, this graph here that I kind of skipped over, But look what's going on. Here we've got an increasing function, but what I want to concentrate on right now is the concavity of that function right there is downward, isn't it? And it's still concave downward. And then this point right here, the concavity changes there, doesn't it? To the right of that blue point, isn't that now concave up? And it's still concave up. All right? So the red part of the graph there, concave down, so that's F. Concave down tells us what about F prime? Decreasing, which tells us what about F double prime? Negative. The blue, concave up, that's F that's concave up. What's that tell us about F prime? Increasing. And what's that tell us about F double prime? Positive. Okay? All right. By the way, that point there where the concavity changes is called a point of inflection. All right? Point of inflection. Look at the facts we have that are in red and in blue, and see if you can figure it out and tell me. Looking at the second derivative, what changes when the concavity changes? The sign of the second derivative changes when the concavity changes, doesn't it? Okay? So that'll give us a place to look for points of inflection. All right? Look at this last graph here. What's its concavity? It's concavity. What's the concavity? Up. All for that whole graph, isn't it? Okay? So if the concavity is up, what's the first derivative doing? Increasing or decreasing? Not that one. And if f prime is increasing, what's the sign of the second derivative? Positive. Okay. Correct. And that's the thing we kind of got to get through our head is we want to know about concavity visually because it is a visual thing. But the definition of concavity doesn't have anything about how it looks, does it? The definition is concave up on any interval where the derivative is increasing, concave down on any interval where the derivative is decreasing. So, yeah, visually we see the concavity up, down. You know, used to we'd say things like concave up, it could hold water, concave down, the water runs off. But that's really not what we want to do, though. We want to go by the definition, okay? So if the slopes of the tangent lines, as you move from left to right, are increasing, that function's concave up. Yeah. Only if the graph is not drawn in a good window for you, okay? Otherwise, yeah, you can tell by looking. You can tell by looking. Correct. Yep, that's right. So here's our test for concavity. And when I write the test for concavity out, I'll do it a little bit differently than the book does. I'll have a nice little table for you again. But all this needs to make sense to you, okay? All this needs to make sense. So we've got a function whose second derivative exists because it's going to be really hard to tell a concavity from the second derivative if the second derivative doesn't exist, okay? So if the second derivative exists, and if the second derivative exists, it's either going to be positive, negative, or zero, isn't it? So first part, if the second derivative is greater than zero, in other words, the second derivative is positive, then that leads to concave upward for the graph. All right, because remember the progression. If the second derivative is positive, the first derivative is increasing. By definition, if the first derivative is increasing, the graph is concave upward. So this line here simply skips that middle step, doesn't it? We know three things go together. F concave up, F prime increasing, and F double prime positive go together. They've just left out the F prime increasing, which is fine. Those three things go together. If you know one, you know the other two, period. Okay? And then if F double prime is less than 0, F double prime is negative on our interval, then the graph is concave downward on the interval. Because remember what goes together. F double prime negative goes with F prime decreasing. F prime decreasing, by definition, means that F is concave downward. Okay? With me? Now, you're probably thinking, I'll never memorize all that. Yes, you will. You will write it down on a piece of paper, and you will stare at it long enough that you will memorize it. And you're going to want to. Right now, I know you don't have it memorized. Right now, does it make sense? Okay, good, good. All right, so F can change concavity only where F prime changes from increasing to decreasing, which means F double prime changes from positive to negative. Or F can change concavity where F prime changes from decreasing to increasing, which is where F double prime changes from negative to positive. So F can change concavity only where F double prime changes signs. And that's what you guys told me, I don't know, here somewhere. I guess it was here, wasn't it? You guys told me that. So the graph of your original function, f, can only change concavity where the second derivative changes signs. Now, think about it. We said that the first derivative, to use the first derivative test, the first derivative could only change signs at the critical numbers, where the first derivative equals 0 or the first derivative does not exist. So if we're looking for places where the second derivative changes signs, can't that only occur where the second derivative equals 0 or the second derivative does not exist? So a point of inflection can only occur where the second derivative equals 0 or the second derivative does not exist. Okay? You got it. All right? So, here in a few minutes, when we go hunting for points of inflection, where are we going to hunt? We're going to hunt where the second derivative equals 0 or the second derivative does not exist. If you're wasting your time over there where the second derivative is always positive, you're never going to find a point of inflection. If you're wasting your time someplace where the second derivative is always negative, you're never going to find a point of inflection. If you're hunting around the place where the second derivative changes from positive to negative, where the second derivative equals 0 or the second derivative does not exist, now you can find yourself a point of inflection. Okay? Now, we call them points of inflection. Sometimes they're not actually points. For instance, if I had a vertical asymptote here, that would be concave up. That would be concave down. And let's say that vertical line is x equals 1. We would say that the concavity changes at x equals 1, but it would be not quite correct to say there's a point of inflection at x equals 1, because there's not a point. See, when you have a vertical asymptote and that happens, not only does f not exist at x equals 1, since it doesn't exist at x equals 1, its derivative doesn't exist at x equals 1, so the second derivative doesn't exist at x equals 1. So it would be a place where the second derivative does not exist, but we're just not going to get a point, are we? And then different people say it different ways. Some people go ahead and just call that a point of inflection. knowing full well that technically they're wrong, it's not a point. Others will try to say that there's a place of inflection. Really, place? Others will just say the concavity changes at x equals 1. And even though that's the wordiest, that's probably the best way to say it, is that the concavity changes there. Okay? So I'll take any of those things, but, pay attention to your college professor, and they may not. You call it what they tell you to call it. All right? All right. Y'all hanging in there? Is your head hurt? Not yet? Yeah. It's not a point of inflection because there's not a point. Okay? Right, like if I can draw one here, like right about there, that graph changes from concave down to concave up. So whatever the coordinates of that point are, that is literally the point of inflection. Okay? And at that point, the second derivative equals 0 or the second derivative does not exist.
So this is more like that.
You can do that too. It works together. Yeah, if you know, well, but the thing is, I'm not going to tell you the point of inflection.
Yeah.
I'm going to tell you to find it.
Kind of see it
On a graph, yes. Yes. On a graph, you can visually estimate the point of inflection, and therefore you can estimate where the second derivative equals 0 or the second derivative does not exist.
Like a point of inflection, the graph of second derivative is like the same thing as a critical number on the first one.
Exactly. The possible point of inflection to the second derivative is the same thing as a critical number to the first. Okay? All right. And there's our definition of a point of inflection. Okay? It's simply where the concavity changes. All right? And again, visually, we can usually come pretty close. Right about there, the graph changes from up to down, which means the derivative changes from increasing to decreasing, which means the second derivative changes from positive to negative. And then here, and then here. And that was a little more awkward when you get that vertical tangent line thing going. That's a little tougher to see sometimes. But we can usually see those, usually. And if you can't, if you adjust your window, then maybe you can. Okay? All right. Let's see. Let's look at the note here. The definition of point of inflection in this book requires that the tangent line exists at the point of inflection, but some books do not require this. So that's what I was talking about with the vertical asymptotes, and they're just flat out telling you they say it one way, other books say it another. We're going to say it any which way. I want you to be familiar with it, no matter where you end up going to college. Okay. So you can have a point of inflection only truly when there's a point, but that doesn't mean the concavity can't change. Then what do you call it? Place, concavity change, different places will say different things. So when the graph of f is concave up, or here's something else, I haven't talked about this yet. When the graph of f is concave upward, the graph is always above the tangent line. And when the graph of f is concave downward, it's always below the tangent line. All right, that's a handy way to look at it. Let's look at it here, this top one. Graph is concave upward at first, and look where the tangent lines would be if you draw them in. So the graph really is above the tangent line when it's concave upward. And then look where it switches to concave downward. The tangent lines are up here now, so the graph of the function really is below its tangent line. I'm glad I saw that there. I'd almost forgotten to mention that. So that's another thing visually you can look for. Okay? All right? So if, this is what you were talking about, knowing the point of inflection first seems a little easier. It is. If C, f of C is a point of inflection, then you know for a fact that f double prime of C equals 0 or f double prime of c does not exist. Anytime you have a point of inflection, the second derivative at that x coordinate of the point of inflection equals 0 or does not exist. Now, just like with critical numbers, sometimes we'd get a critical number, but there was not a maximum or a minimum at that critical number. Nothing happened. The graph kept increasing or it kept decreasing. Just because you have a place where the second derivative equals 0 or does not exist doesn't prove that the concavity is going to change there. You can get false positives is what it amounts to, okay? So, but if the concavity changes, it only changes where the second derivative equals 0 or does not exist. But we have to test them all, because just because the second derivative equals 0 doesn't necessarily mean the concavity is going to change. All right? All right. Then on your note page, I've summarized all of that, hopefully in a way that you can read and understand and begin to memorize. Okay? That's all the concavity stuff right there. All right. Questions? Comments? Okay. Now, we can use the second derivative to find maxes and mins. Okay? What's called the second derivative test will help us find relative maxes and relative mins. Now, there are some conditions here. First off, if the second derivative is really difficult to find, and all they're asking you is for the relative minimum or the relative extrema, the first derivative test may still be the best way to go about it. But you have a polynomial. The second derivative is usually right off a polynomial function. All you got to do is use the power rule a time or two to get its derivative. The derivative will be a polynomial. Use the power rule a time or two again to find its derivative, which is easy to do, and we can use the second derivative test. So one restriction on the second derivative test is if the second derivative takes you 2 pages to find, I'd use the first derivative test. Okay? And also, the second derivative test only works for the critical numbers where the derivative equals 0. Okay? Because there's 2 ways to get critical numbers, right? Where the derivative equals 0 or does not exist. But think about it. For the critical numbers where the first derivative does not exist, if the first derivative does not exist, neither does the second derivative. Okay? It can't. If the first derivative does not exist when x equals 12, well then the second derivative does not exist when x equals 12. So the second derivative can't tell you anything about what's happening at x equals 12 because the second derivative doesn't exist at x equals 12. Okay? So the second derivative test only works where the first derivative equals 0. So it only works for those critical numbers. But here's the way it works, and it's really nice and neat and easy to do when it works. If the second derivative is greater than 0, that means the second derivative is positive. If the second derivative is positive, what's the concavity of the function? Up. So, if the second derivative is positive, our function's concave up for that whole interval where the second derivative is positive, right? Now, if we knew there was a critical number where the derivative equaled 0, derivative equals 0 means horizontal tangent line, doesn't it? Okay? So if the second derivative is positive where the first derivative equals 0, that means we have a relative minimum. Follow me? Second derivative is positive means concave up. Derivative equals 0 means horizontal tangent line. So if both of those things are happening at one place, you've got concave up and a horizontal tangent line, it's got to look like that, which means you have a relative minimum there. Mm-hmm. And then you flip all that around. When the second derivative is negative, that means concave down. The first derivative is 0. That means horizontal tangent line. You've got yourself a relative max. Okay? Yeah. If the derivative does not exist, then don't try the second derivative test. Okay? Only try the second derivative test where the derivative equals 0. I can't emphasize that enough, because otherwise you're just wasting your time. You're not going to get a conclusion. Okay? All right. So that's the second derivative test. It doesn't always work. It's not always practical. But when it is practical and when it does work, it's really quick and easy. Okay? Any questions on the second derivative test? All right, let's look at these graphs. The one on the left, the second derivative is positive. I know that because the graph is concave upward. Right there at x equals c, the first derivative is negative, the first derivative is 0 there, isn't it? So, when the second derivative is positive and the first derivative equals 0, that sure looks like a relative minimum right there, doesn't it? And then look at the second graph. The second derivative is negative. I know that for a fact because that graph is concave downward. And then there at x equals c, the first derivative equals 0. I know that because there's a horizontal tangent line there. Visually, yes. Visually. So that sure looks like a relative maximum, doesn't it? Okay? All right. And then, again, on your note sheet that I gave you, I've got the second derivative test, hopefully written in such a way that it will make some sense to you. All right, I'm ready to do a couple of examples. Any questions before we do that? All right, good job. This is not the easiest thing to spend time thinking about. You guys hung in there, hanged in there, stuck with me really well. That's it. All right, so turn to page 195. And we'll start visually. Let's start with number 6. Number 6. Now, they give us the equation, the function that they've graphed here, and I don't care. I'm going to use the graph. All right? So, on number 6 here, the directions tell us to determine the open intervals on which the graph is concave upward or concave downward. So when we go from negative infinity, start at negative infinity, and you're moving to the right. So you're going along the graph here. Even though the function's decreasing, this is concave up, isn't it? And it's concave up until about right there, right? Everything I have in blue appears to be concave upward. That looks to be about -2. Now, am I 100% positive that it's -2? No. Okay? But visually, it sure looks like it's about -2. So from negative infinity to -2, our graph is concave upward. And the words are really upward and downward, even though we usually say and write up and down. It's supposed to be upward. All right? And then, so right there at x equals -2, we have a point of inflection. And then it sure looks like the graph, well, it is. The graph is concave downward now. And it's concave downward how long do you think? Till 0? So from negative infinity, no, sorry, from negative 2 to 0, concave downward. What does our next interval look like to you? From 0 to what? Looks like 0 to 2. And from 0 to 2, concave upward. And then are we good from 2 to infinity? 2 to infinity, it's never going to change again, is it? So from 2 to infinity, concave down. Now, they don't ask us to state this, but since the concavity changes at x equals negative 2, there's a point of inflection at x equals negative 2, and at x equals 0, and at x equals 2. Yeah. Right. If they ask us about extrema, we're going to have a relative minimum right there, whatever that x-coordinate is. We're going to have a relative maximum right there. No. Yes. Yes. Because it all goes back to that definition. Because, let's face it, these people that figured out calculus, they're pretty bright. And they figured out that, to avoid traps later on, they have to define things very carefully. So they did not define concavity visually. They defined it by the derivative increasing or decreasing. Okay? So that was not an accident. All right. Number 6 makes sense? All right, number 12. Find the points of inflection and discuss the concavity of the graph of the function. All right, so they give us a polynomial function, that's good. F of x equals 2x cubed minus 3x squared minus 12x plus 5. Recall the points of inflection, the concavity changes where the second derivative changes signs. So we got to find the derivative, then we got to find the second derivative. That's why I'm glad this is a polynomial. So finding the first derivative, use the power rule on each of those terms. So f prime of x equals 6x squared minus 6x minus 12. All right, the big reason we needed the first derivative is because we needed to get the second derivative. Now get the second derivative. What is the second derivative? All right, so f double prime of x equals 12x minus 6. And kind of like I would usually do with the first derivative, unless I just forget, I'd really like to go ahead and factor that. So we're going to factor that, get 6 times the quantity, 2x minus 1. Now, just like we wrote several times, critical numbers occur when f prime of x equals 0 or f prime of x does not exist. We don't have a nice little term like critical number. So I write it this way. A point of inflection can occur only when f double prime of x equals 0 or f double prime of x does not exist. And I know it's monotonous writing that over and over, but I want you to, because that idea needs to be drilled into your head. Now, when we're using this in February for something else, you don't have to write the sentence. Right now, I really want you to get that drilled into your head, okay? Well, the second derivative is a polynomial. It exists, doesn't it? But if I set 6 times the quantity 2x minus 1 equal to 0, what does that equal? 1/2, okay? Take as many steps as you need to work that out to get x equals 1/2. So f double prime of x does exist. X equals 1/2 is a possible point of inflection. So if the concavity does change, it can only change when x equals 1/2. Concavity doesn't have to change, but if it does, that's where it does. Make sense? All right. Now, I write out a little table as my test for concavity, and it's going to look familiar to you because it's got an interval, a test number, but instead of sine of f prime, it's sine of f double prime. And then we'll reach a conclusion. All right, now, what would be the appropriate intervals for us to be worrying about concavity for this particular function? From negative infinity to 1/2. Because, remember, the only place the concavity can possibly change is at x equals 1/2. So go from negative infinity to 1/2, and then what's your other interval going to be? 1/2 to infinity. And then pick you out a nice easy number to work with in each interval. I use 0 whenever I can. 0 fits nicely into the first interval. I just pick 10. You can pick 1,000,000,000 if you want for that second interval. All right? And then I use my second derivative because I don't care about the value of the second derivative. I care about the sign of the second derivative. So if I go back to just right here, there's the second derivative, isn't it? And if I put a 0 in for x, what do I? No, I don't get 0. I get a negative number because 2 times 0 is 0. 0 minus 1 is negative 1. 6 times negative 1 is negative. So I get a negative second derivative. What does that tell me about the concavity of the original function? Up or down? Down. Concave downward. Concave downward. Abbreviations are okay. Be careful to abbreviate too much. Some people just put the first letter of a bunch of words and they end up with nonsense. Okay? Concave down. That's correct. All right? Now, use your other test number. When you put a 10 in here for x, now what do you get? Positive second derivative or negative second derivative? Now it's a positive second derivative. We don't care what the number is. We just care if it's positive or negative. Concave, up. Now, so it's a lot of work leading to it. But I really hope that the test for concavity itself makes sense to you. Okay? I mean, you got to do a lot of stuff before you get to it. But second derivative positive, function concave up. Second derivative negative, function concave down. The only place the concavity can change is when the second derivative equals 0 or second derivative does not exist, because that's the only place where the second derivative can change signs. Second derivative can't just magically change from positive to negative without either equaling 0 in between or not existing in between. All right. Now, the directions actually wanted a point of inflection. So now that I know the point of inflection occurs when x equals 1/2, what do I do to get the point? Plug it into the original function. So you can use your calculator if you want. And so when x equals 1/2, the original function equals negative 13/2, or decimals are okay. Don't give me decimals, have to, but decimals that terminate are all right. Don't round things off unless you really have to. Okay? So 1/2 negative 13/2 is I could have put the point of inflection. There can't be another one. Not for this function. That right there is your discussion of the concavity. Okay? And see, that's the thing. You know, you always are going to have to show your work. Next year, for me, on free responses on the AP test, and that's where these tables work out really nicely. Because looking at this table, we're discussing the concavity of the graph right there, circled in red and circled in blue, aren't we? Okay? So discuss doesn't necessarily mean write sentences. Well, you see how I got the 1/2? Take the 1/2 and plug it in there, there, and there. Okay? All right. Any questions? Okay. Now, there are actually 2 more examples I want to do. There are the assignments that we're going to do from this section. I haven't shown you an example of the second derivative test yet for finding relative extrema. But some of those you can do. So if you want to go ahead and get some of those knocked out of the way, it's just going to help you later on. All right?